these are some formulas, standard formulas for electric potential. From its center, so first one, at its axis, V equals to 1 by 4 pi epsilon naught P by R square. Second one, at equatorial position. At equatorial, V is 0. See, when there is an equatorial position, V will be 0. Means overall V will be 0. Because it is equatorial. Okay, equal positioning. A point having coordinate r and theta. With respect to center of dipole. V equals to 1 by 4 pi epsilon naught P sin theta. No, let P cos theta. It should be P cos theta. So at a general point having a coordinate r comma theta with respect to center of dipole, due to system of charge, V equals to V1 plus V2 plus so on till Vn. So it will give you summation of I equals to 1 till n 1 by 4 pi epsilon naught Qi by Ri. Then this 1 by 4 pi epsilon naught is constant. So let's bring it out. We are left with Qi and Ri. So in Qi Ri, let's take it as 1, 2, 3, 4 till n. 4 pi epsilon naught Q1 by R1 plus Q2 by R2 plus Qn by Rn. Done writing? These 3 points, did you write? Some standard formulas for electric potential. Make a note, come on. First one, due to point charge Q at a point distance R, which is standard formula 1 by 4 pi epsilon naught Q by R. Next one, due to short electric dipole at a distance R from its center. So at its axis, P by R square. P is dipole moment. Dipole moment, P equals to Q to L. Okay. At equatorial position, V will be 0 because summation of everywhere it will be same because it's equatorial. Okay. So at general point having coordinate r theta with respect to its center of dipole, it will be P cos theta by R square. Now this 3 was about a short electric dipole at a distance R from its center. Now third one, due to system of charges, V equals to V1 plus V2 till Vn. So summation of all this will give you Qi by Ri 1 by 4 pi epsilon naught. So I can be 1 to n. Done writing, everyone?
Yes, sir.
Okay. Those who joined just now, finish writing? I am making a note of it. Varsha?
Yes, sir. Finish writing.
Finish writing? Okay. Adesha joined from starting, right? Beginning of class?
Yes, sir.
So you wrote, I think so, right?
Yes, sir.
Okay, super. Let's go for next topic. Excuse me. Okay, so till what we wrote? Formula for equipotential surface, potential difference. Okay. Okay. Equipotential surface. Now, just now I gave you small explanation. Can someone explain this? Try. Try it. It's okay. Right or wrong, but try it. What is equipotential surface? Anyone?
Sir, from the word equipotential, it can be seen like where the surface which will have all the same electric potential.
Okay. Okay. Surface will have equal potential. Okay. Yes, Divya, you're about to say something.
Yes, sir. It is.
Yeah. Go on.
They are always perpendicular to electric field lines.
Okay, so they are called equipotential. That's what you're saying.
The first point, another one said, sir. So I continued the second point.
Okay. Okay, so first point is similar to Adyashas, right? That's what you're saying.
Yes, sir. Or we can say it is the collection of points like in space that are all at same potential.
Okay, at the same potential. Okay. Yes, anyone else want to try? Varsha, Sai Charan, Pawan Kumar, Jafar, Dairya. Anyone want to try or answer? No one? Okay then. Let's try it. Yes, the answer is correct. And equipotential is that it has same potential everywhere. Potential at each point. So they are called equipotential, equal potential surface. Generally, the conductor which is charged, they are equipotential. Charge conductor in equilibrium is a equipotential surface. Yes, everyone understood? Which are equipotential surface? Varsha? Which are equipotential surface? Varsha, tell me. Is not connected to audio.
It has same electric potential at each point.
Yes. It has same potential. Now, let's talk about energy now. We saw this equipotential, then let's talk about energy now. Potential energy. I'm not able to write. Now, what is potential energy? Yes, anyone? What is potential energy? Sai Charan, what do you mean by potential energy?
Sir, can I?
Yeah.
Sir, electric potential is the amount of work needed to move a unit charge from a reference point to specific point against an electric field, sir.
Yes, very good. Okay. Then what is potential energy, Divya? Potential energy.
So can I?
Yeah.
So the energy possessed by the particle by virtue of its position, sir.
Position. Virtue of its position. Or another way. Yes, correct. That is correct. Any other way?
It is a type of energy by which an object has because of its position, sir.
Position. Yes, like virtue of its position. Yes. Or other way is like a stored energy.
Yes, sir. Stored energy that depends
Yes.
upon relative position.
Relative position. Correct. So, as we are saying, it is a stored energy. That's what we are going to discuss here. So, if there are two charges, if Q1 and Q2 are two point charges at suppression R12, 1 due to 2. 1, 2 means 1 due to 2. Then electric potential energy U equals to 1 by 4 pi epsilon naught Q1 Q2 by R12. This is potential energy of electric. That means electric potential energy. U is electric potential energy. If there are n point charge Q1, Q2 and Qn, separation is Rij between ith particle and jth charge particle. So it can be 1, 2, 3, 4, whatever. So I equals to 1, 2, 3 till n. And j should be next number 2, 3, 4, n. Next. It should not be 1, 1, 1, 2. 2, 2, 2, 3. I mean 2, 3, 3, 4. The next number. So summation we can give as U equals to 1 by 4 pi epsilon naught. It will be common outside. Summation of I and j should be more than 1. Qi Qj divided by Rij. For the ith particle. Once you're done writing, tell me. I'll go for next.
Done, sir.
1 minute, sir.
Yeah, I'll be waiting.
Done, sir.
Okay. Okay. Then let's go for next. With energy only, we are going for next part. Electric potential energy of a dipole. In uniform electric field. So in uniform electric field, potential energy of a dipole will be minus PE cos theta, or we can say minus P vector E vector. It's minus. We are not going with derivation. Because in your competitive exam, we don't require derivation. We require formulas. Now for work done, this is for potential energy. Work done of a dipole or in rotating dipole in uniform electric field, and the angle will be same thing I'm saying, whatever is the heading, same thing I'm saying. Work done on rotating dipole in uniform electric field from inclination theta 1 to theta 2. So work done equals to change in potential energy. That you remember 11th standard, cos theta 1 minus cos theta 2. I will change this minus sign inside. So suppose in this case, if dipole is in stable condition initially, if dipole is initially stable, equilibrium, position, and theta 1 equals to 0. So we have W equals to PE 1 minus cos theta now. Let's take theta 2 as theta now. Anyhow, just remember, not all this formula. This formula is enough. PE cos theta. And W equals to PE cos theta 1 minus cos theta 2. And in this one, we don't need to remember this one, just standard formula, this. U equals to K Q1 Q2 by R12. R12 means R in the sense like distance between those two charges. I guess today we'll finish this not capacitors, not possible. We'll start capacitors, no. Let's see. Maybe tomorrow, day after tomorrow. Done? Once you're done, tell me. I'll move for next. Done writing, everyone? Is anyone still writing or shall I scroll?
Done, sir.
Okay. Now tell me, what do you mean by conductors? What are conductors? Yes, what are conductors?
Which have free electrons in it.
Which have free electrons in it. Then what are insulators? What are insulators then? Conductors are having free electrons in it. Okay, correct. Then what are insulator?
Which have low electrical conductivity, sir.
Okay. So do they have free charge carriers?
No, sir.
They don't have free charge carriers? Okay. And conductors have charge carriers, right? Free charge carriers. So that's why they are allowing current to flow easily. Then if I ask you, what are semiconductors then? Will they allow free charge? Do they have free charge carriers? Will they allow current to flow easily? Someone answer these two questions. Yes, anyone? Varsha? Are you there with us?
Yes, sir.
Yeah. So what are semiconductors? Okay. Sai Charan?
Sir,
Yeah. What are semiconductors?
materials which have conductivity.
Conductivity. Materials which have conductivity. What? Complete your statement.
Materials which have conductivity between conductors and non-conductors.
Okay. By non-conductor, you mean insulators.
Yes, sir.
Okay. So do they allow current to flow easily? Okay. Tell me anyone tell me like what is the speciality about semiconductors? What is why do we have so much hype on semiconductors? Okay. No, they don't allow. Yes, Jafar, yes. I want to answer what is the specialty of semiconductors? Why we are saying it's very, very important than conductors and insulator? Why semiconductors are so important? Think and tell me. I'll ask you again. Till then you think. Till then I'll write a few statements which you said just now, conductors and insulators. See, what's the question? I'm repeating again. What is the specialty about semiconductors? Why is so important?
They can be used for conversion of energy, sir.
They can be used for conversion of energy. Okay. Give some specific. Yeah, you are right. That is correct. But I want what is specialty? Something which is important for conductor. That's why we are using it. Something is important in conductors.
They act both as conductor and insulator, sir.
Okay, correct. So when they will act as a conductor? Yes, yes. This is the answer. Come on. When they will act as a conductor? When there is an electric field passing through it. So important of semiconductor, why we have so much hype about semiconductors? When we pass some electric field, they will behave as a conductor. Especially like we are talking about silicons and germanium, right? You have heard those two mostly, right? Silicon and germanium. Okay. Now there is a question: do insulator also behave as a semiconductor? Some case.
Sir, can you repeat the question once?
Can this insulator behave as a conductor or a semiconductor in any case? Okay, somebody wrote answer. Wait, let me read. Yes. Correct. At very high temperature. Yes.
Temperature, sir.
So it can behave, but at very, very high temperature. For some case, it might not be easily, we cannot reach that much temperature, or some case we can. Okay, so let us finish this first. Then let's come back to insulator. So semiconductors are substance which contains free electrons, or not say, don't say electrons, let's say charge carriers. And they allow easily, due to freely availability, they allow easy flow of current. Insulator are those which does not contain free electrons or free charge carriers, and do not allow freely. Let's take do not allow flow of current. Let's write one important point about it. The electron or free charge carrier inside a metallic conductor positive fixed, and they are bound in charge carrier. And are bound in charge carrier. Electrons are freely charged carrier inside the metallic conductor, while positive ions are fixed and are bound charge carrier. So difference between metallic conductor and electrons and positive ions. Positive ions does not move. That's what they are saying. Electrons are freely available, freely moving charge carrier.
Sir,
Yes.
can you once explain what is meant by this fixed bound charge carriers?
It is
Fixed
fixed
and a
position.
bound charge.
Yeah. Fixed means like they are wherever they are, they will be fixed position. They are not moving. Charge carrier means it's just a carrier. Like it will be in that it will be positive ions, negative ions. Negative ions, we know that we have given name as electrons. So electrons are freely charged carrier, which is freely moving, and positive ions, they are fixed type. Electrons are free type. Positive ions are fixed type. In metallic conductor, everything will be there, positive and negative, obviously. Because it's made up of some atoms. So atom has both things, positive and negative. So negative V says electrons, and they are freely available, and positive ions, they are fixed. Name itself. This name itself, we are given name same way, like positive ions are fixed. Okay, fixed and or bound carrier, charge carrier. Bound means like whatever it has, it will be fixed position. They are bound there. And electrons will be freely. ठीक है?
Yes, sir.
Okay. Then shall we go for next topic? Next is dielectric. Okay, shall I scroll? Okay then. Dielectric. Now, what is dielectric? We were using here in last chapter K constant. Those constants are named as dielectric constant. Now it has some fixed value. Now what are dielectric? How we are using? How it is made? Let's see that. Let's write some point wise. First one, like insulator are often referred as dielectric. Even dielectric is made up of atoms and molecules. Same thing. Okay, so that is understandable. So in some dielectric, positive and negative charge centers coincide. Means what? In some dielectric, positive and negative charge coincide. So in that, those dielectric are named as, or are said, are given name, particular name. Let me change color. Okay. Such electric are said to be non-polar dielectric. While in some other, they coincide. So they are called polar. Positive and negative charge do not coincide. Such dielectric have permanent electric dipole movement. So are said to be polar dielectric. So let me show you some dielectric, a photo, so that you can understand better. Okay, these are just diagrammic. No, I want actual photo. Okay, by the way, have you seen capacitor any day? Have you opened that capacitor inside? Did anyone tried? Anyone? See, these are the different shapes of dielectric. Okay, so what is the importance of this one? As we pass high electric field, it will conduct, but a very little amount of conduction. Once we pass electric field, high amount of electric field, it will just conduct a little bit. So that's why they are said to be, a first line we wrote, they insulators are referred as dielectric. So even most of the things like when you're in capacitors, inside the capacitor there is some rubber thing or some stuff they are fixing. It's not the rubber actually. That is a dielectric. So are said to be polar dielectric. Okay, we'll see more detail about this dielectric tomorrow. First, you finish this writing. Because we need to understand more about dielectric. Any doubt in today's session? Anyone?
Yes, sir.
Shall I stop sharing?
Yes, sir.